Welcome to today's Explainer. If you've ever stared at an algebra problem and felt like you were trying to decipher some ancient forgotten language, well, trust me, you are absolutely not alone. Today, we're diving straight into our source material to strip away all that confusion. We're going to look at algebra for what it truly is, a beautifully simple and honestly highly satisfying mechanical process. So let's jump right into the mechanics of math, specifically how to solve one-step equations.
Okay, this quote right here, this is our starting line. And it isn't just a gentle suggestion. It is literally the absolute foundational philosophy of algebra. I want you to picture a classic set of balancing scales. The equal sign in any math problem is the exact center point of that scale. If you drop a heavy weight on the left side, the scale tips, right? To fix it, you absolutely have to add the exact same weight to the right side. That delicate balancing act is the entire secret to mastering equations.
Here's a quick roadmap for our explainer today. We'll start with the golden rule, then dive into using inverse operations, collecting like terms, tackling real-world word problems, and finally, proving your answer. Let's get to it.
Step 1. The golden rule. Let's unpack what balancing actually looks like in practice.
When you look at an equation, I really don't want you to just see a random string of numbers and letters floating around. I want you to see a rigid, perfectly balanced structure. Our main goal in algebra is to isolate the unknown variable, usually x, so we can finally figure out what it actually is. But as we manipulate the numbers around it, our primary job is to keep that entire structure from tipping over. Whatever mathematical procedure you apply to the left side to get x all by itself, you must, without exception, apply to the right side. Balance is everything.
Moving right along to Section 2, using inverse operations.
So let's talk about the actual tools we use to solve these puzzles. The crucial thing here is understanding what an inverse operation actually does. It's really just the exact opposite mathematical operation. Think of it like being a detective. Your variable is your unknown suspect, and it's surrounded by all these other numbers. To find out who your suspect really is, you have to strip away those attached numbers using deductive reasoning. You use inverse operations to literally undo the math that's tying those numbers to the variable. Think of equations as giant, intricate machines. Inverse operations, well, they're the gears that let you run that machine in reverse. If someone built a machine by turning a crank forward, you figure out how they did it by turning the crank backwards, right? You're just reversing the process to isolate your core variable.
So how exactly do these gears pair up? It is beautifully logical. Addition and subtraction are inverses of each other. If a variable has a number added to it, you just subtract that number to undo it. Simple. Conversely, multiplication and division are a pair. If your x is being multiplied by 5, you just divide by 5 to undo it. By applying these opposite actions and, of course, remembering our golden rule of doing it to both sides, we elegantly peel away the layers.
And this perfectly illustrates the mechanical, repeatable process we've pulled right from our source material. It's a foolproof 4-step algorithm. Step 1, identify your variable. Step 2, identify the operation happening to it. Step 3, apply the exact inverse operation to both sides. And Step 4, calculate your final value. If you follow this exact sequence, I promise you this machine will spit out the correct answer for a one-step equation every single time. It completely takes the guesswork out of the picture.
All right, Step 3, collecting like terms. What happens when things get a little messy?
Sometimes, before we can even whip out our inverse operation tools, we gotta clean up our workspace. The big idea here is that equations can look incredibly intimidating simply because they're cluttered. Before you even try to isolate your variable, you need to look at both the left and right sides of your equation and gather up the pieces that naturally belong together. It's exactly like sorting your laundry before you toss it in the washing machine.
Let's see how this actually works. If you're staring at a long equation with multiple matching variables, don't panic. Just combine them using basic math. By following these simple steps, a complex, scary-looking string of items collapses right back down into that simple one-step format we already know how to solve. You're really just organizing the data. Now, let's shift gears and look at Section 4, real-world word problems. Because hey, math definitely doesn't just live on a whiteboard. Check out this contrast. On one hand, we have strict, structured geometry, like finding the unknown angles of a triangle. On the other hand, we have a delicious chocolate chip cookie. So what on earth do they have in common? Algebra is the hidden engine behind both of them. We can use the exact same one-step equations to solve a theoretical geometry puzzle as we can to figure out a real-world shopping scenario.
Our source material gives us some fantastic everyday examples. Whether it's weighing the cost of a fresh batch of cookies for Kira or figuring out the exact value of a stack of mixed coins for Sabrina, these aren't just random stories. There are literally variables waiting to be isolated. We can translate these everyday mysteries into an X, set up our balanced scale, apply our inverse operations, and mechanically find the exact truth of the situation.
And finally, we arrive at our last section, proving your answer.
In the mechanics of math, this is our quality control department. In algebra, a solution to an equation is often called the root. Finding that root is exactly like hitting the absolute dead center bullseye on a target. But the absolute best part about algebra, and I truly mean the best part, is that you never have to guess if you hit the target. You can actually prove your accuracy with 100% certainty before you ever hand in your work.
So how do we do this? Through a substitution check. And let me tell you, it is incredibly satisfying. You just take your final value for your variable and you plug it back into the very original equation. Then you just do the math. If your left side perfectly equals your right side, say 10 equals 10, you know definitively that your answer is correct. The scale is balanced, the machine worked perfectly.
Now, to wrap up our explainer today, I want to leave you with a fascinating little quirk from our source material to chew on. We've talked all about finding the one exact root, right? But what happens if you encounter the equation 0 times x equals 0? Why does that specific, weird equation have infinitely many solutions? Think about how any number in the universe interacts with 0. Keep that mystery in mind the next time you turn those mechanical inverse gears. Thanks for hanging out with me for this explainer, and keep questioning the mechanics behind the math.